Broadcast is now starting. All attendees are in listen-only mode.
Hello and good afternoon, everyone. My name is Anna Zylik and I am with ICF. We are the vendor working on behalf of Energize Connecticut to bring these Passive House trainings to all of you. So thanks for joining us today for this Passive House webinar. A reminder that we are recording this training and we will make this available afterwards. These trainings are at no cost thanks to the sponsors of Energize Connecticut. These trainings are also in partnership with Connecticut Passive House. A reminder that the Energize Connecticut program is offering a 50% cost reimbursement for professionals pursuing either FIAS or fee accreditation trainings. And this includes the cost of the trainings and the exam. So once you become certified, we'll work with you to process the 50% cost reimbursement. With that, I will pass it over to Keegan, who's also with ICF, to talk about the Connecticut Passive House building incentives.
Thanks, Anna. Yeah, and welcome everyone. Thanks for joining today. So in addition to the Passive House training initiative that you all are taking part in today and the accreditation reimbursement through Energize Connecticut, the sponsors of Energize Connecticut are also excited to offer new construction incentives for multifamily buildings with 5 units or more that choose to pursue Passive House certification. Aaron, if you want to go to the next one. The incentive structure is a really innovative structure that allows builders and developers and other stakeholders working on these buildings pursuing Passive House certification to really defray some of the costs for pursuing the Passive House certification, and has benchmarks along the way for participation in the program. So if you're interested in learning more, there's some information at the bottom of the slide, and we can share that again as well upon close. But with that, I will introduce our speaker today, Aaron Gunderson, and turn the mic over to him. Hi, Aaron.
Hello. Thank you, Keegan, and thank you, Anna. It's great to be presenting here to a Connecticut audience. Thanks to all the great folks at Connecticut Passive House for all the work that you've done down there. I'm with Passive House Massachusetts. So we work, primarily up in Massachusetts, but we've done a lot of New England area events as well. So I've seen some of you I've seen in person years ago when we could be doing in-person events, and I hope to see you all again here in the future. But today I'm thrilled to be presenting to you virtually here. So we're going to go through this Passive House 102 session, as it's called, that's focusing in on multifamily buildings. We're going to talk about some design and construction concepts related to them. So really, this is still sort of an introductory level presentation. We're not going to go too in depth, but I'm going to cover a lot of stuff. So we're going to talk a little bit about the Passive House standard itself and kind of what the Passive House metrics are. We're going to talk about some kind of common design and construction elements, so things related to the building envelope and air tightness of these various buildings. We're going to go through some examples of projects. So I have quite a few from Massachusetts that I've been familiar with, and I have a few from Connecticut that folks have shared with me that I'll talk a little bit about as well. And then we'll end with some lessons learned from some of the projects teams that have worked on some of these projects, some of the things they want to share with others who are embarking on possibly their first Passive House project. So here you're seeing just sort of a scatter shot of different Passive House buildings. I just like to show this slide at the beginning to just refresh everyone's mind that Passive House doesn't mean a single family house. It means all types of buildings. Really, it's passive buildings. Anything can be a passive house. We have large multifamily buildings, as you can see here. We have a small single family net zero home there in the right corner. The sort of the middle bottom screen is a university residence hall. And then the right corner is actually an office building going up right now in downtown Boston that will have around 750,000 square feet of passive house space. So all different types of buildings can meet the passive house standard, not just homes. So today we'll talk a little bit about the multifamily residential aspect of it, but a lot of the strategies apply to buildings of all types. As I go through this, feel free to use the sort of chat room and question feature here of GoToMeeting to ask questions, and I'll try to address anything that you guys have. At the end, we'll dedicate a lot of time to questions, but feel free to type them in as I go through this as well, and maybe I'll address them then if appropriate. Otherwise, we'll wait to the end. But I want to see some interaction from folks and really want to talk about the things that you guys are really interested in hearing. So a quick refresher on what PASSIVEhouse is. So it is a performance-based building certification standard that focuses on the reduction of energy use. And you can see for space heating, cooling, well, ensuring comfortable, healthy, low carbon building. Really the takeaways here are in orange. It's performance-based, so there is a set of actual performance metrics in terms of energy performance. So for example, kBTUs per square foot of the building that you can use in energy. We'll talk a little bit about those. That's sort of one of the key aspects, is performance-based. And the other is that it zeroes in on energy use. So there's lots of great holistic sustainability standards out there that address all types of things from land use and water use to all different types of aspects of sustainability. PASSIVEhouse is really focusing on the energy part of it. So it's narrowing in on space conditioning and then addressing the overall energy use of the building as well. So what you achieve by getting buildings certified to PASSIVEhouse is you're achieving dramatic reduction in overall energy use. Obviously, as I just mentioned, that's sort of the point. But really where that comes from is the desire to reduce carbon emissions that are, from the fossil fuel energy sources we're using to power our buildings. So you're achieving that reduction in energy use and then the corresponding reduction in carbon emissions. We're also seeing a proven improvement in air quality, occupant health, and occupant comfort. These are some things I won't talk a lot about today. I have a couple slides where I'll talk a little bit about them. But the reality is this is becoming an increasingly important reason that folks are going with PASSIVEhouse, both in terms of why, say, tenants are looking for PASSIVEhouse units, why developers are interested in building to PASSIVEhouse standard, issues around air quality, controlled ventilation. These things are coming up more and more. So it's a good thing to keep in mind about the benefits of these buildings. We're also seeing greater building durability. So simply buildings that are built better, last longer, resist mold and rot and some other issues that can cause buildings to fail. We're seeing greater resilience to major weather events. I'll talk a little bit about what I mean by this in a moment. Lower operating costs. Of course, if you're reducing your energy use from your utilities, you're going to have lower utility bills. We're also seeing slightly lower, say, maintenance costs. You don't have a lot of the old say natural gas boiler systems for heat that can break down a lot more often than these newer electric systems. And then lastly, a pathway to net zero. So PASSIVEhouse standard by default is not a net zero standard, but many projects use it as a platform to become net zero. Once you drop the energy use so dramatically by achieving PASSIVEhouse, a lot of projects can more easily achieve net zero that way. You can have a lot of roof space to get solar panels on there and bring you down to net zero. So we'll talk a little bit about that here today too. But I want to hit on this air quality, health, and occupant comfort. So just kind of a little bit more what I mean by that. So PASSIVEhouse projects deliver continuous ventilated filtered air. So you have these ventilated systems coming in and they're passing through high MERV rated filters and you're getting fresh air in the buildings. You're also seeing an increased use of non-toxic materials. So that's not a part of the standard, it's not a requirement, but it tends to be just sort of a byproduct of the attention being paid to these projects. Consistent and comfortable room temperatures. This is part of what PASSIVEhouse achieves, is by having that really consistent envelope that keeps the heat in and having a really efficient heating system. You're able to make sure that there's no drafty areas in the room, that the area next to the window is not colder than the area next to the door. Elimination of air drafts, so those air leak areas in the building envelope where air can come in, cold air can come in the winter, you're eliminating those. You see an increased use of natural lighting. So like the materials part of it, this is more of a byproduct. PASSIVEhouse puts a premium on solar heat gain, so say solar heat coming from the sun, and that leads to a tendency to have increased natural lighting compared to a traditional project. And then you're also seeing quieter acoustic conditions. This has been brought up by more than one person to me who lives in a PASSIVEhouse about how they didn't realize how much quieter it would be. This is both in terms of outside noise, whether that's the garbage truck on your street or a car horn going off, that your big thick envelope that's keeping the heat in, it's also keeping that noise out. And then the equipment in there, whether that's the heating equipment or the water heater, they tend to be a little bit quieter in terms of operation than your traditional equipment as well. So you have less noise being produced inside the home. Durability and resilience. So a little bit about what I mean by this is the ability to shelter in place. So say you have power outages, things that may affect your heating equipment or your cooling equipment. your building is able to maintain your temperature for a lot longer when that's out. We've seen this summer actually in some buildings where we had some power outages this summer on really hot days. Your electric AC went out. Well, if you were in a PASSIVEhouse building, your building stayed cool for a lot longer until the electricity came back on. Some other things here about resilience. This sort of like indoor air quality is becoming a larger issue and a bigger talking point as one of the benefits of PASSIVEhouse. And then, as I mentioned, a pathway to net zero. So this is a little bit more about this, what I mean. So most buildings, as you can see, even those built to stretch codes, reach codes, advanced building codes, still use too much energy on site to reach net zero. PASSIVEhouse solves this by drastically reducing the amount of energy demand for the building. And that means that there's going to be enough space to provide enough energy to be net zero. So you can see that the picture here is actually the Bullitt Center out in Seattle. You all may have seen this before. It's been around for a while, a great example of sort of a holistic, sustainable building. But they had a goal of net zero in mind, and they realized that in order to achieve it, they had to be built to the PASSIVEhouse standard. Otherwise, those solar panels you see hanging over the building, they built that to sort of the traditional code in Seattle. It would have been an entire block's worth of solar. So not possible for them. By going to PASSIVEhouse, they were able to fit the solar panels there with a little overhang and achieve their goal of net zero. So energy reduction. So now I'm going to kind of zero in on this sort of main aspect of PASSIVEhouse that we all sort of focus on, is the ability to reduce energy demand in the building. What do I mean by that? So in reality, we're looking at a 90% or greater reduction in heating and cooling loads compared to a typical building. This isn't just sort of a lofty goal that projects try to achieve, because PASSIVEhouse is a metric-based system. This is what PASSIVEhouse projects are achieving, 90% or greater reduction in heating and cooling loads. In addition to that, we're also seeing anywhere from 40 to 70% reduction in overall energy use. That varies more greatly from building to building, but beyond heating and cooling loads, we're seeing the overall building energy demand go down as well. And there are metrics related to that I'll show you in a moment too. So show you some examples of actual projects and kind of what we're achieving. So this is the distillery. This is a project in Boston. It was actually the first multifamily PASSIVEhouse built in Massachusetts. And this is, you can see the sort of the energy use. So this is going by energy use intensity, or EUI. It's just kBTUs of energy per square foot of the building. And this is overall energy. So this is not just heating and cooling. This was looking at plug loads, appliances, all of that together. The distillery hits 24. Overall, the sort of Boston general area code, kind of for the Boston area, hit about a 62. And then in general, the kind of greater cold climate Midwest or mid-rise region in the Northeast was 53. So you can see distillery was a pretty significant improvement over those. Here's one up in New Hampshire. This is Guilford Village. This was actually a senior housing complex that was built up there. You can see the improvement that they have. So they actually did this in phases. Phase one was just sort of a typical construction, but then phase two, they met LEED. So that was their goal, to kind of hit the LEED standard. Then when they went to phase three, they went ahead and hit the PASSIVEhouse standard. You can see the improvement. And I like showing this one because the difference between a phase three and phase two is simply that they hit PASSIVEhouse in phase two or phase three. They did a few extra, detailing around air tightness and some other things to hit that. But the overall sort of design of the building wasn't any different than the one that hit LEED. They just paid a little bit closer attention to some thermal barriers and air barriers in order to hit it. But by doing that, they were able to achieve that drastic energy use reduction. And another example, this is from Philadelphia. Philadelphia has sort of been out ahead in terms of PASSIVEhouse project, especially on the multifamily affordable sector. Their financing for affordable projects included benefits for PASSIVEhouse earlier than any other state. So we've seen a lot of projects there. And here's kind of a comparison that we've seen. You can see on the graph, the gray bars on the left are the PASSIVEhouse projects, and you're seeing around a 25 average EUI. And then you have LEED projects in the Philadelphia area at a 47, and then you're sort of code your typical construction buildings up there at about 50, 59 or so. So again, no matter where we see these projects being built, New Hampshire, Massachusetts, here down to Philadelphia, you're seeing drastic improvements. So I just wanted these slides to show you that this, goal of energy reduction is not, a hypothetical goal that we're still striving to figure out how to do. It's a reality. You build a PASSIVEhouse standard, and you know that you're going to have really high performing building. And we also seen, because of the impacts Passive House has, especially around a lot of the financing initiatives that have been coming out, like these great incentives that Connecticut is introducing, is a huge growth in Passive House. So this is data from FIA. So this is just FIA's projects, but you're seeing kind of the Northeast region. So you got Massachusetts, Pennsylvania, New York, and Connecticut. You can see for a while, New York was a huge leader. Massachusetts has jumped up quite a bit the last few years, in part because Massachusetts introduced their financial incentives, which mirror the ones here in Connecticut. Connecticut, you can see the green is growing up, 2021. Nice growth there, jumping up from where it was before. And I hope to see that now with these incentives rolled out, that in the future years, 2022, 2023, that green bar is going to be up right there, right where that blue bar is in Massachusetts. Maybe you'll be above it too. We'll see. This is just showing you some of the Mass Save incentives. So Mass Save is what the incentive programs are issued under in Massachusetts compared to the Energized Connecticut ones in Connecticut. This is just showing you kind of the growth. So the incentives were introduced in 2020. In 2018, you can see that little blue thing there, that little blue dot, that's the distillery, that one multifamily building that I was talking about, the only one that existed in the state. When the incentives were introduced, you can see this sort of huge growth in the number of projects and the number of units that they introduced. So Connecticut, you have a lot to look forward to with these incentives. Now, talk a little bit about cost. So these are all Massachusetts examples. That's just where I have a lot of cost data for, but it's worth sharing because I think you're going to see similar numbers in Connecticut. But these are all affordable housing projects in the state. This is from the Mass CEC, which did a Passive House Design Challenge. Their goal was a 3% cost premium for their projects. And you can see all of them are below that, some significantly. So you got Finch Cambridge up there in Cambridge, Massachusetts, a 1.4% cost premium. You can kind of see all the others here. But a great reality that we're starting to see is that the cost of these projects has come down dramatically. It's pretty confidently in that 1% to 3% range in terms of cost premium over a typical project. We're hoping that comes down to par. I've heard it in Pennsylvania, they've had that much closer to zero sum on a lot of other projects. So cost is not a big driver compared to what it used to be. And when you factor in the incentives that are now available, you're able to, kind of bring this cost premium down to, well, effectively, well, I'll let you figure out what that means for your project, but it's a really great deal. So what does it mean to achieve Passive House? So a little refresher on the Passive House certification requirements themselves. So they're based on sort of two buckets: performance criteria and then sort of other criteria or soft criteria. I'm not going to go too in depth on the criteria today. There's a whole other presentation to really dive into the metrics, and that's not really the focus of today, but I do kind of want to bring them up briefly so we all are on the same page on what Passive House is going for. So the performance criteria is based around heating, cooling demand. So how much energy, whether that's electricity or however you're powering your heating, cooling equipment, how much energy you use. There's a max amount you can use. Whole building air tightness. This is actually measured through a blower door test on site. So you have to have an airtight building envelope. And then source energy demand. This is the metric for overall energy use of the building. And this is in source energy. So for those unfamiliar, there is, when we talk about energy demand of a building, we usually talk about it in terms of site energy or source energy. Site energy is the amount of power, amount of electricity, and energy you're using on site. The source energy is how much is being produced, say, at the power plant. And generally, it's around 2 to 3 times greater at the power plant than it is at your building because of energy losses in transmission. So what that means is that the source energy is actually greater than the on-site energy. So when we look at overall energy use, we're looking at that source energy metric, because that's the one that determines how many carbon emissions are being produced because of the energy we're using. So that's the important one. The first building, the building that is in the photo here is actually in Germany, and this was the first sort of Passive House building that was sort of built. It was, in many ways, the prototype for the Passive House standard. Still running great today. And what I liked about it is a multifamily building. So those haven't seen it before. I mean, I know here in the U.S., a lot of the very first Passive House buildings were single-family buildings. But what they did in Europe and especially in Germany is they sort of started with a lot of multifamily buildings. So in many ways, we're still catching up to what they've been doing in Europe since. Well, this was built in the mid-90s, so been going on there for a while. So where does the certification come from? Where do you get your stamp of approval for a PASSIVEhouse building? It comes from these two organizations. You have the PASSIVEhouse Institute, which is based in Germany, and is the one responsible for this building you're seeing. And then PHIUS, the PASSIVEhouse Institute US. They're based in Chicago. Both of these organizations certify buildings here in the US. So whether you're in Connecticut or you're anywhere else in the country, you can certify a building through either PHIUS or through PHI. So we see projects going through both of them in Massachusetts. Some go through PHIUS, some go through PHI. I know in Connecticut, you've seen the same thing. Some projects go through PHIUS, some go through PHI. This is something you'll work, with your PASSIVEhouse consultant and kind of with your team on and figure out which one you're going to go for. But either one works. They're very, very similar in terms of what their metrics are, in terms of what they require. They just have some minor differences. But they both create and manage their own PASSIVEhouse standard. So they have their own set of metrics for what a PASSIVEhouse means and what you have to hit to be one. They both define those metrics, define the other kind of soft criteria that I was mentioning. They also provide the certification, so you can be certified for either one. And they both provide accreditation for professionals. So if you want to become, say, a certified PASSIVEhouse consultant or certified PASSIVEhouse designer or trade person or so on, these are the organizations you can be certified through. And they both provide their own training and both of their own sort of certification methods for that. And I should kind of, to what Keegan and Anna were mentioning at the beginning, the incentives that are available apply to both of these standards. So whether you meet, the PHIUS standard or the PHI standard, you qualify for the same incentives. So what are the metrics? So this is just an example. I want to be very clear about that. When you're building to the PASSIVEhouse standard, you're going to work with your consultant, work with whichever of these organizations you're going through to get the exact metrics you want to hit. So I'm just bringing these up as an example so we can sort of get an idea of the energy demand we're talking about. So this is a PHIUS metric. So I'm using the PHIUS Plus 2018 standard. They recently updated theirs, and they're sort of in an overlap period right now where you can use the new one or this old one. Then you sort of have the PHI standard there on the right, which is more of a universal standard that doesn't change as often. So what you're seeing is, and the numbers here are sort of for the Massachusetts area climate zone. Connecticut would be slightly different than this. But again, they're useful for just kind of getting an idea of what we're talking about. So annual heating demand, you can see 5.3 kBTUs per square foot if you were going to the PHIUS standard. If you were the PHI standard, about 4.8 kBTUs per square foot. So very, very similar. When you look at, the average existing building, say even just a single family home is probably in the 60 kBTUs per square foot range for heating demand. So pretty significant reduction. And when you get that far, these two numbers are very, very similar to each other. The bigger thing to kind of understand about them is that the PHIUS metrics are climate specific, so they sort of vary depending on where the building is located. And the PHI metrics tend to be more universal. So those numbers tend to kind of be, they just tend to remain the same no matter where you're building the building. The other thing that kind of varies in how they calculate source energy. PHIUS uses kind of a combination of area and by person. So if you're building a residential project, including multifamily residential, their metrics are sort of in a kilowatt hours per person, whereas PHI tends to stick with the overall energy by size of the building. But again, either way, kind of the same. On the right, you're seeing just an example of these demands being calculated for a PHIUS project. This is actually the Auburndale Builders office located in Newton. It's just a one-story office building. They actually renovated it. So it was an old garage that they turned into a PASSIVEhouse office and a net zero office at that. But you're seeing, and this is coming from WUFI, which is the energy model that tends to be used for PHIUS projects. PHI projects use sort of a similar looking one called the PHPP. But either way, you're modeling the energy use of the building, the energy demand. You're plugging all sorts of factors into it to try to figure out how much energy your building's using. You're sort of seeing, this is showing you that they're hitting their heating demand, cooling demand goals, all the way down to source energy. So this gives you an idea of they're hitting their targets. But that's sort of the output that you're seeing. This is really all I'm going to talk about, specific metrics. So again, if you have questions, definitely ask them and I can get into them. The last metric I want to talk about is the air tightness standard. So the ones I just mentioned are all measured through modeling and then through some verification on site to make sure everything built to the way it was modeled, but it's being measured through modeling. Air tightness is being measured on site through a blower door test. And this is sort of giving you an example. So the PASSIVEhouse standard looks for about 0.6 ACH 50. So that's air changes per hour at 50 pascals of pressure. Basically, that means you're pressurizing the building and measuring the amount of air leaking through the building once it's pressurized. A 0.6 is a pretty strict standard. You can see that generally, if you go kind of the building energy code, the base energy code, you're going to have about a 3 air changes per hour. So this is a pretty significant improvement. And when we get to multifamily buildings, this is where we're seeing the focus of the team, of both the design team and the construction team. This is really the metric they're focused on hitting. Those other metrics, the heating demand, cooling demand, source energy demand, you're going to really work that out in the design phase and the modeling phase and figure out how you're going to hit those, what equipment you're going to use, how much insulation, for example. You're going to kind of figure out how to hit those metrics. This metric really depends on both the design and the construction. Really need to make sure that on site, everything's being constructed well, being constructed properly, everything's being done, seams are being taped, penetrations are being sealed up. This really becomes a focus of the project team throughout the entire construction phase to make sure this metric is hit. And I'll talk a little bit more about that as we go through this and show some examples. So what are the features of passive house buildings? How are projects actually going and hitting the standard? As I mentioned, this is a performance-based standard, so all you have to do is hit those metrics. There's not really a checklist of specific things you have to do, types of insulation, amount of insulation, R values. There's no specific requirements on those things. Instead, there's sort of a set of design features that teams have come up with to hit this. And that's kind of what I'm going to cover. I'm going to kind of go through these, show you some examples, show you how teams have sort of hit these metrics. But the features are continuous thermal insulation. So that's insulation in the cavities and insulation wrapping around the whole building. Thermal bridge-free construction, which honestly should be just a reduction of thermal bridges. You're always going to have some thermal bridges, but really you want to reduce the impact of those thermal bridges. An airtight envelope, as I mentioned, you're hitting that 0.6 ACH metric. High-performance windows and doors, better quality windows and doors. Optimized solar heat gain, which I briefly mentioned this, but you want to increase the amount of sunlight coming into the building, providing heat, but you want to optimize it so you're getting that heat in the winter months and you're not getting it in the summer months. We'll talk maybe a little bit about that as we go through this as well. Balanced ventilation. So you're making these buildings very, very airtight. You're putting that big sweater over the building, but then these buildings do need to breathe, and they're breathing through a very controlled way, just like your body breathes through your lungs, not through other holes in your body. The building needs to breathe through a very controlled way, and that's through a ventilation system. So I'll talk a little bit about what buildings use there. Efficient and minimized mechanical systems. So your heating and cooling systems, you still have systems, even if you're reducing heating and cooling loads by 90% or 95%, you still have something that's producing your heating and cooling. But you're using efficient systems, minimized, so they're smaller systems. So we'll talk a little bit about that as we go through this as well. So first, just go through some overall design concepts. So things you want to keep in mind from the very beginning. So massing and form, just sort of the way that the building looks. Really, this is just getting at the concept that a simpler form tends to be easier. So your sort of typical square block building or rectangle block building is going to be a lot easier to hit the standard than ones that sort of have a lot of various things jutting in and out of them, a lot of corners and various different connections. All those different connections and corners and things where buildings jut out are places where you're going to introduce thermal bridges, you're going to introduce breaks in your air barrier, and places where you have to kind of connect that air barrier. So they become challenging areas. So the simpler the form, the easier it's going to be. Building orientation. So because we focus on that solar heat gain for part of the heat, you do want a large face of the building towards the south so you can get a lot of sunlight. But you do want to watch out for the summer months because you don't want to get too much sunlight. We've seen some projects that don't consider their sort of summer heating from the sun, and they overheat in the summer months. So this is that Auburndale Builders project I was showing you earlier, and they just have their solar panels there on an awning, and that's the south side of the building. That awning blocks out some of the sunlight in the summer months, so they don't overheat the building. But it's high enough so that in the winter the sun can go into those front windows. So that's an example of orientation, sighting, and kind of keeping in mind the shading mechanisms you need to use in the summer. And increased density. This is especially true for multifamily buildings, but the denser the building, the more heat sources that you're going to have, and it tends to mean the less insulation you need on the outside of the building to keep that heat in. And the more sort of traditional envelope you can have versus a really thick kind of old school passive house envelope. This is just an example. This is the Distillery and Finch, Cambridge. You can see below you. This was the same architecture firm, Icon Architecture, that worked on this. Some of the same folks. They use very similar methods in terms of air tightness. They use the exact same continuous insulation material, in this case mineral wool. Biggest difference is that at Finch, they went down to 2 inches of mineral wool versus 3 inches. A lot of reasons for that, but one of them was the greater density of Finch. and glazing percentage. So this is getting at your windows and your window placement. So just like in terms of having those windows on the south side so you can get some of that sunlight in, you also want to be considered consider how many windows you're having, how much percentage of your glazing you're having. This is both because of that sunlight issue, but also because that window area is going to be a weak area in your wall. Even when you're using high performance windows, high U factor windows, or low U factor windows, I should say, that's still going to be a weak area in your wall. No matter how well you have that window put in and installed, it's going to have a lower or it's going to have a greater thermal conductivity than the rest of your insulated wall section. So reducing the amount of those windows is going to be important. Showing you here, this is finished Cambridge again, and this is actually getting a little bit at the awnings. I just wanted to show you because the side of this building that's facing kind of towards the center of the image is the south side. You can see the little awnings that are over the windows. On the east side of the building, the one facing away from kind of to the outside of the image, they don't have awnings in those windows. Even though the east side is getting some direct sun, especially early in the day, through their calculations, through their modeling, they determined that it wasn't a big enough factor for them to have to put awnings there. But on the south side, it was. So they put awnings there. So let's dive into some of these a little bit more in depth. Excuse me. So I'm going to talk about the building envelope. So the main principles, so I kind of mentioned a few of these already, but you have that thermal barrier around the building. That's what the building envelope is providing, this thermal barrier. That is being done through continuous insulation on the outside of the frame, and then through a dense packed cavity insulation. So whether you have that wood frame cavity or a steel frame cavity, you're dense packing that space with insulation. Typically, we see either fiberglass or cellulose. I've also seen mineral wool being used inside the cavity, spray foam. So there's other things you can do, but I would say fiberglass and cellulose is definitely the most typical. Kind of a theme, as I've sort of hit on, is the larger the building, the lower the R value, the more heat sources you have in the building. For example, the greater heat production, the less insulation you have on the outside, so you can get away with a smaller amount of insulation, but you still need to wrap the building in some type of continuous insulation. The building envelope is also going to be airtight with a dedicated air barrier system. I'm going to talk more about that in depth. And then a reduction of thermal bridging, and I'll talk more about that as well. Here below that, you're seeing some sort of typical values of the R value and insulation levels for this climate zone. And I want to emphasize that this is just typical values. These are not requirements. Again, there's no requirement for the specific R value or the amount of insulation beyond what code requires for Passive House. Beyond code, you're simply doing what you need through your modeling to hit those Passive House metrics. But what we tend to see is this. So you tend to see about walls that are around 40 to 50 R value with total insulation of about 10 to 12 inches, and that includes your cavity insulation and your continuous insulation. And again, this is just typical. And as you get to a bigger building, as I mentioned, you're going to see a reduction in this, especially in that insulation inches. You tend to see that shrink. So just things to keep in mind there. Let's talk a little bit about air tightness. So, I'm actually going to go back. I want to show you this image. So what you're seeing here, this is the distillery, but just kind of explain what you're seeing. On the very top of the image, you have the green material there. That is zip system sheeting. That's being used as sheeting material and an air barrier for this project. Zip system is an air barrier as well. The green part of it that's on the outside of the sheeting that's built into it is an air barrier. And then the black lines that you see going across the green part of it is the tape system. So they're taping all the seams. And when you install that properly, it works as an air barrier. Then on top of that air barrier, you can see the brown material that's kind of in the rest of the photo, the light brown material, that is the mineral wool continuous insulation. So this is what they put 3 inches of on the outside of the project. On top of that insulation, they're putting a rain screen, and then they're attaching their siding. What the rain screen does is it provides a small gap in between the siding and the insulation. That allows the mineral wool to dry out when it gets wet. And the whole assembly, I should say, can dry out that way. So air tightness. So the main principles of air tightness is that you're having a continuous air barrier around the whole building. You're eliminating any gaps and holes in that barrier, any penetrations. You're taping all the seams, you're taping those penetrations, you're kind of covering it all up, making sure that that air barrier is continuous. And as I mentioned, you're measuring your air tightness on site with a blower door test. Here's sort of 3 examples of air barrier systems. Elm Place, that's a multifamily project up in Vermont. They use zip system. So you can see, again, zip system going up there. The material you see going on outside of the zip system is their continuous insulation. It's actually the white part of that is a foam board, and then they have the sort of the wood on the outside of that. But the green fabric, the green material, is their air barrier. Then you have in the middle here, you have this is actually a single family project, but it's an example of an interior air barrier. The vast majority of projects that I've seen, especially multifamily projects, are using an exterior air barrier. So it's going on the outside of the envelope. But there are some projects that do the opposite and put it on the inside. And this is one example. They're using Intello, so that's the white fabric that you're seeing. So they have their cavity on the other side of that. The wood members you're seeing here going up outside of the air barrier or on the inside of the air barrier is just a service cavity. So that's not even going to be filled with insulation. They'll just put their drywall over that and it'll be empty for a service cavity. But the white fabric is providing their air barrier. And you can see they're taping all the penetrations. And you can see an example of how the tape can look kind of funny sometimes. It's all over the place. And that's good. You want it to kind of look like that because that means you're taping everything. On the right, the far image, you're seeing Finch Cambridge, and this is where they're using SIGA. So SIGA is an air barrier membrane system that they you put up on there, and then you tape all the seams. You can see them right now doing a very, very good job of taping that properly. A lot of good attention to detail to make sure that tape is applied properly. A concept with sort of air tightness to keep in mind is something called the red line test. You may have heard this. This just means, can you draw a continuous line around the project, without lifting up your pencil to show your air barrier. It's just emphasizing the fact that there's no gaps in that air barrier. On the left, when you kind of are doing it to your whole building, it's pretty easy to kind of just go around and do it. But when you zoom in on some of the connections and transitions, that's where it becomes, really important. And this is just showing you that sort of, you kind of have the window to wall connection, the wall to roof connection here. Very critical places. So you really want to make sure that when you kind of zoom in on these drawings, you're really getting to these really key areas that air barrier is being focused on and highlighted, and everyone knows where it is, and it's continuous throughout the whole thing. Thermal bridging. So thermal bridging is simply weak areas in the building envelope where you have material that has a higher thermal conductivity than your insulation. So this is things like wood studs, steel beams, metal fasteners, a lot of plumbing lines, electrical lines, things that are going through the envelope. All these type of things are places where your envelope is being weakened and you have something being introduced that transmits heat and thermal energy a lot better than your insulation does. So you can see in the image is showing you a wood stud building, and you can see the wood studs. You can also see the fasteners as well. That gives you an idea of the heat loss going through that type of material. But thermal bridges not only lead to heat loss, they lead to greater problems in these buildings. So they lead to lower surface temps on the interior wall. They impair thermal comfort. So you have colder areas near the wall than you do in other places. I mentioned one of the benefits of PASSIVEhouse is that consistent room temperature. Thermal bridges are in addition to air leaks is where you see that not happening. If you have too many thermal bridges, your outside wall is going to be a lot colder. Impaired thermal comfort, I mentioned, risk of condensation and risk of mold growth. So by having those lower surface temperatures, you increase condensation risks on windows, you increase mold growth potential. So a lot of problems can be introduced with thermal bridges. So we want to reduce those and mitigate those. So how do we do that? Well, there's insulation outside the frame, so that continuous layer of insulation. That's not just adding to the thermal envelope of the building. It's also breaking up those thermal bridges. So these wood studs that I mentioned, you're not going to eliminate wood studs in a building. You might use some advanced framing methods to use fewer wood studs, but you're still going to have them. So how do you reduce the thermal bridging impact of those? Continuous insulation. On the outside of the project, that continuous insulation is providing a break there. It's obviously not eliminating thermal bridge, but it is reducing the impact that it has. So that's a way to do it. Areas of concern. So kind of things to focus in on are going to be the weak points in the insulation, so the studs, as I mentioned, wall penetrations, as I mentioned, but also beams that can pass through the wall, outside features that get attached to the wall, so your balconies, your awnings, some of these other architectural features that get attached. Those are places where you can introduce thermal bridges to the wall. Corners are a big area. They tend to be a weak area in the envelope, where you tend to have a greater amount of studs or other type of materials that have lower thermal conductivity or higher thermal conductivity compared to insulation. And then your window frames are a big area as well. So these are kind of things that really focus in on for your thermal bridging. Sort of in another example of mitigating measures. So On the left, you're seeing this is Finch Cambridge, and this is how they attach their mineral wool insulation to the outside of the building. They use these clips. These are Cascadia clips, the red things that I'm talking about here. And those are allowing a way for them to attach the mineral wool without having a large metal fasteners going through the whole project, through the whole wall. So again, it sort of reduces the thermal bridging and allows you to attach your insulation without having a lot of thermal ridges. Elm Place, that Vermont project I mentioned a bit ago, so they had what we see in a lot of multifamily projects, are they had a steel frame sort of garage space platform, and then on top of that they did wood framing for the actual the rest of the structure. But that sort of steel to floor connection is a huge thermal bridge problem. So how do you do that? How do you kind of get around that? So you can kind of see in this image, there's on top of the vertical steel beam that's going up, there's this little lighter gray disc, and that is a thermal break. It's sort of a different material. It's there to kind of provide a thermal break. Heat is still going to transfer through there, but it's going to be greatly reduced from what it would. So these are some kind of methods, but they're ways to introduce thermal breaks to areas where you simply can't avoid thermal bridging. So now I want to talk a little bit about heating and cooling, and then I'll get into ventilation. Again, if you folks have questions, please type them in here and ask them. So for heating and cooling, we're pretty much seeing air source heat pumps and VRF heat pump systems across the board. It's definitely the most common. There are other things occasionally being used, but this is with confidence I can say this is what projects are doing. What heat pumps do, for those unfamiliar, is they provide efficient electric heating and cooling. So they do both heating and they do cooling. They operate at around 200–400% efficiency. So what I mean by that is you can kind of see this image in the heating season showing you how it works. Rather than, say, with a natural gas boiler, you're taking natural gas, you're burning it, and you're using that to produce heat. So you're taking the kPDUs of that natural gas, and that's going to produce heat, and you have some losses from that. So even your most efficient gas furnace, it's only going to be around 98% efficient. You have some losses there. The heat pump takes electricity from the grid, but it doesn't use that electricity to produce heat. It uses that electricity to run a compressor that compresses air and takes heat energy from that air and transfers it into a coolant. So the heat energy isn't coming from the power source, from the electricity, it's coming from the air. And that's how you're able to achieve a greater efficiency, 200–400% efficient. The coolant then transfers it into a head on the inside where it's released back into the air as heat, and it works in the opposite for winter months. These can be centralized, unitized, ducted, ductless. There's lots of ways to hit them up. What we're seeing in a lot of projects is while it's pretty consistent, they're using some type of heat pump or VRF heat pump system. How that's being designed is not consistent. We're still seeing some multifamily buildings where they have a heat pump unit in every single unit. We're also seeing some projects where they have sort of central units. I'll show you some examples here. So this is Finch Cambridge. What they did is a VRF condensers on the roof. That's what you're seeing in the image next to there. And they connected heat pump heads in each unit. So they had around 13, actually I shouldn't say around, they had 13 rooftop condensers on the units that went into 149 different heat pump heads. So these were heads that were in each, they had 98 units, so 98 living spaces in the building, but then 149 heat pump units. And what that meant is some units had more than one. They also went to common spaces, things like that. But that was sort of a way to centralize their heating and cooling system. The distillery did individual heat pump units for each unit. So this is a photo of their roof. They had one of those condensers. So this is an image of 4 of them. They had one of them for every single unit. So they had 28 units in that building. So they had 28 units on the roof, and those all fed into a heat pump head in each of the units. And in this case, each unit had one heat pump head, and that heat pump head was installed in the roof somewhere in the unit and then ducted to the living spaces. So these are sort of 2 different methods, and this is sort of what we're seeing with heating and cooling. You're using this sort of VRF or heat pump units, but whether you centralize them or unitize them in some way is still kind of varying from project to project. Ventilation. So as I mentioned, these projects definitely need to breathe. As you've all heard the old adage, homes need to breathe. Well, it's true, but they need to breathe controlled. And we do that through a heat or energy recovery ventilator. So HRVs or ERVs. These are systems that are continuously running, so they're providing ventilation into the building at all times. They can have variable speed, so they don't need to be operating at the same. So the fan doesn't need to operate at the same speed all the time, but they're always going to be running. And they're providing fresh and filtered air into the building. So they're pulling air from outdoors. They're bringing it into the system that you see this sort of drawing of. It's passing over a filter. So it's being filtered, and the newer systems have high MERV rated filters, so you're getting some high quality filtered air. That air gets passed over a heat exchanger. So it is transferring energy from the incoming air to the outgoing air. So say in the winter months, when your interior space is being heated, you have the exhaust air from the interior space being pulled through the vents, going into the system, going through the heat exchanger, where some heat is being taken out of that air, and that is being transferred to the incoming air. That incoming air is cold, coming from the outside, but it's being a little bit preheated by this transfer of air. What this means is that you're not mixing air. So a lot of traditional ventilation systems will mix incoming and outgoing air. You're not doing that in these systems. That way you can ensure the air quality aspect of the incoming air, because you're not mixing it with the interior air. But by passing over that heat exchanger, you're able to recover some of that heat energy and reduce the need to reheat that air to get it up to temperature again. And these systems, I mean, when I talk about recovering heat energy, we're talking about 80% or greater heat energy recovery. So they're very, very efficient at recovering heat energy. The main difference between so there's two of them, the HRVs and ERVs. The main difference is that ERVs, so the energy recovery ventilators, tend to also provide some level of humidity control. So say in that winter months, they're going to provide some humidity from that warm air. They're going to take some of that humidity out of the warm air and be able to sort of transfer it to the cold air. So they have some level of humidity control. So we tend to see them more used in our climate zone, tend to be ERVs, more common. Just like with just like with heat pumps, the bigger question is not what do you use, because it's ERVs and HRVs, is how do you install them. So this is sort of an example of the various methods that you can do. This was put together by Peterson Engineering, so I thank them for this, but you sort of see three general concepts. So there's unitized, or local, as it's sometimes called, and this is where you put one ERV in every single unit. So this is what the distillery did. Then one of these units in every single unit. So if I actually go back, this image of a Zender unit you can see here, this is what they had. So they had a closet in every single unit that had one of these systems inside of it. You then had sort of a hybrid or floor by floor approach. So Mattapan Station, that's a project going up in Boston right now that's doing this approach, where they have they actually have 3 ERVs on each floor, and each of those ERVs are being ducted into multiple units. I think, maybe 4 or 5 units for each of them. But that's a floor by floor approach. And then you have your centralized approach. And this is what Finch did, where you have one of those units on the roof that goes down into a bunch of different units within the building. So you're going to different floors. In the centralized approach, in this case, obviously you had more than one VRF unit on the roof, but the key is that those went to multiple units in the building. So this is sort of the three, sort of the 3 methods we're seeing. You're going to work with your mechanical engineer on sort of how to design this. And this is one of the key reasons you want to bring a mechanical engineer into the process early. You want to integrate them into your team from the very beginning, so you can figure out what method you're going to use. What we've seen is performance-wise, there isn't really any variation. You're going to be able to hit your PASSIVEhouse metrics no matter which one of these, methods you use. The performance has been about the same. The key sort of concepts of why you go to one or the other tend to be, which types of units you want to use, maybe what your mechanical engineer is familiar with. Bigger reasons might be your duct network. Where are these ducts going to go? How are they going to, kind of fit throughout your project? You got to think about that and kind of build in that space. Maintenance is another issue. So these things will need some maintenance from time to time. They will need filters changed every year. Sometimes multiple times a year, so you're going to need access to the units. So these are the type of things that you want to consider in terms of how you place this and what type of method you come up with. But energy performance is going to be pretty similar. So now I want to go through some examples. I have a lot of Massachusetts examples. I have some Connecticut ones that folks have shared with me. I'm going to talk a little bit about them. Then I'll go through some lessons learned. And again, ask questions about any of these that you have. So this is Finch Cambridge. This was completed in 2020. This is 98 units, all 100% affordable housing, different income levels, but 100% affordable. Icon Architecture did this. You can see all the other information there from the other parts of the other folks on the project team for your info. I'm going to talk a little bit more about sort of how they did it. So this was 2x6 wood studs, They dense packed fiberglass inside the wood studs. Then they use, as I mentioned earlier, 2 inches of mineral wool on the outside. So I'm just going to show you some of the images first. So you can see that top image, that is the SIGA air barrier membrane. So that's what they use for their air barrier. So they had their 2x6 wood studs on the inside. Then they put a sheathing material on the outside of that. And then on top of the sheathing material is where they attach this air barrier membrane. This is not like a wood membrane. The air barrier is just like this, a sheet membrane that you put up there and you tape all the seams. You make sure it's flat. You make sure it's sealed tight on the sheathing, and you tape every seam you possibly can to make sure that it's airtight. You see then the image below that I showed earlier. This is the insulation then going up on top of that, being attached to those clips there. You can see a little bit more about what they did to the roof and the floor. Again, this is floor over garage. So they had a steel frame garage there, a concrete garage, and then they put the wood frame building on top of that. So they had a lot of insulation on top of the concrete. So 6 inches of XPS insulation. That's a foam board insulation that was needed to provide the thermal break and thermal insulation levels they needed transitioning from that garage, which was outside of the passive envelope, to the passive space. And you can see the air tightness that they hit there, 0.05. So this is the metric there, air tightness CFM 50. That's just another way of looking at air tightness. I mentioned that the goal is 0.6 air changes per hour, 50 pascals of pressure. When you do it through the CFM 50 metric, you're really looking at about like 0.06 or so is what they really wanted to hit. So in this case, 0.056, they did it. This is Harbor Village. This is going up in Gloucester, Massachusetts right now. Actually, I should say they are finishing this up right now. It's a multifamily affordable housing building, 30 units. You can see the folks who did this here. But I want to talk a little bit about how they did this 2x6 wood studs, dense packed with cellulose in this case. They did rigid foam boards on the outside and that SIGA membrane. So they used the same air barrier system as they did on this one as they did on Finch. And when I say they, I mean Icon Architecture, so the same architecture firm. The biggest difference, so why they went to the rigid foam boards. So when you see the pink material, that's the rigid foam boards. Why did they use that on this project versus mineral wool on the other one? A lot of it actually had to do with this brick siding. This is a thin brick, a siding material that went up on the outside. And it really needed a sort of a stronger material to attach to. So they wanted to use the foam boards versus the mineral wool. That's one of the reasons they went with the foam boards. That just shows you kind of a different type of insulation material you can use. I would say that the 3 big ones that we see are mineral wool that I've been showing you in a lot of projects, these foam boards, and then polyiso boards. Polyiso is just another kind of foam board that you see on a lot. It's usually foil faced. So you might see on the outside of a project, you'll usually see it kind of glimmering in silver. And I think I have another project to show you that uses that. So this is Tracy Community Housing. This is up in New Hampshire. This is multifamily, 50-50 between affordable market rate. You can see some other things here. But I like this project because both the developer and the architects, the Twin Pines Housing and Clay Architects, their focus from the very beginning was hitting net zero. They wanted this to be a net zero building. And they came into Passive House actually later in the project timeline because they were struggling to figure out how to hit net zero. They were having a tough time with it. And eventually they came about Passive House and realized that by building it to Passive House was the way they were going to actually achieve a net zero. So they ended up hitting the Passive House standard and getting this certified and being a net zero project at that. In fact, you can see at the top, the solar panels hanging off the top. But you can also see that sort of black material going across the siding. Those are solar panels as well. So they put solar panels on the outside siding of the building as well. Here you can see it going up. You can see in the top image, they're using the polyiso material I was just telling you about. That is the foil sort of silver project you see going up there. So they use 2x6 wood studs. You see that going up down there. I wanted to show you an image of the wood studs going up simply because the wood framing, it's pretty traditional. So if you're working with, say, a GC who's sort of new to Passive House, one of the questions they always, have is what's different? What's different from what they do traditionally versus Passive House? When you get down to the framing, it's not a whole lot different. You might space out your studs a little farther. You might do 24 inches on center versus 16 inches on center. Introduce some advanced framing methods to reduce, headers and some things that are causing a lot of thermal bridging. But in general, the framing is pretty similar to what they do on traditional projects. The sheathing tends to be pretty similar as well. In this case, this project used this dense glass sheathing. The dense glass sheathing going up there. They also use zip system. So you can see in the image, and I can't remember exactly why this project switched between the two of them, but on one side of the building, they use zip system, which is brown in this image. And on the other side, they use this sort of dense glass sheathing. But in both cases, that's pretty traditional. And the reality is we're seeing zip system used in a lot of non-PASSIVEhouse projects at this point, that a lot of GCs are very familiar with it, even those who don't build PASSIVEhouse. On top of that, they put their continuous insulation. So that's the polyiso. The biggest thing they did, and kind of keep in mind though, is you can kind of see in this image if they're overlapping polyiso. So they use 4 inches. So one of those boards is 2 inches thick. So they put 2 boards on top of each other, but they staggered them. You can kind of see that in the image where there's 2 rows of boards, and then the third row you're seeing is actually the one underneath those others. You can see how it's kind of staggered. That's kind of important when you're doubling up on the boards you put on the outside the insulation. You want to kind of stagger them like that, whether that's on the outside of the envelope, whether that's the under slab insulation. If you're putting multiple layers of insulation under the slab, staggering them is critical to make sure the seams aren't lined up. That reduces the chances of air leaks going through it. On the bottom, you're seeing just a little bit about how they did their air barrier then, and some of the siding. But the blue fabric you kind of see in that image is their air barrier. That is another SIGA air barrier system membrane that went on the outside. They put those wood furring strips there as a rain screen, and then you can see them attaching, in this case, hardy board siding to that rain screen. That's how they did it in this case. So let's kind of go on here. Oh, you can also see in the image them doing a very, very good example of sealing the window there with the siding. Let's see. Oh, sorry. There we go. Kind of shift building styles here to go a little bit to a college residence hall. Just wanted to give you an example of a building that wasn't just sort of a standard multifamily building, but a slightly different version. This is a university residence hall for Wheaton College in Norton, Mass. It was completed in late 2019, had its first students that fall. Did not have as many students in 2020 as I'm sure you can imagine why, but has gone back to having some students there now. But a very great place, getting a lot of great feedback from students for the space. But this is a steel frame building. So kind of shifting from all the wood ones we've done before to show you a steel frame project. And I really want to bring this up to show you that there's not a whole lot of difference when you're going from a steel frame to wood frame. They did very similar things. In fact, if we go here, let's see, do I have the next image? Yep, here we go. So you can kind of see this is the steel frame going up. They then put sheathing material on it. In fact, you can see the yellow, that's just that dense glass sheathing. So we've seen that used in a wood frame project already. On the outside of that, they're putting, you can see there the air barrier. The blue material there is the SIGA air barrier system. So they're using very similar sheathing material to wood frame projects. They're using the same air barrier system as wood frame projects have used. And then on the outside of that, they put up their continuous insulation, which you can't really see in these images, and I apologize for that. They did a lot of that while the outside was covered up, so you couldn't really get too many good images of it. But they use the mineral wool insulation, so the same material we've seen in a lot of other projects. The biggest difference you may note here is that they use 5 inches of mineral wool, compared to, for example, Finch Cambridge using 2 inches. Why? Because the steel frames provided a greater thermal bridge. So that's kind of the biggest difference when I say, the materials are pretty similar between steel framed and wood framed. Well, they're going to cause a greater thermal bridge. So you need, in this case, you need to use more continuous insulation on the outside to reduce that thermal bridging impact. But otherwise, very similar method of actually doing this. Now let's get some Connecticut examples. Thanks again to Connecticut PASSIVEhouse for sharing some of these with me. A lot of these were newer to me, so I have less to say about them. Maybe a lot of folks on this call today can actually share some more information because I'm learning about these too, and I'm very impressed by some of the work that's going on down there, and I'm really excited to see what happens with these incentives now in place. This is 11 Crown Street. So this is, I'm showing you the townhouses here, but this was a combination of townhouses and a multifamily sort of a apartment building. It's So 3 buildings in total, 63 units in the apartment style, and 18 in these townhouse rows, all passive house. So really kind of a mixed project here where they did a bunch of different methods. In the townhomes, the ones in the image, they did 2x6 wood frame, fiberglass bats. They did 4 inches rigid insulation, so that rigid foam on the outside. You can see some other things that they did there, but really kind of impressive project that they were able to do a combination of these townhouses and these apartment buildings as well at the same time. This is Oak Tree Village. So this one is being done in phases. This is, let's see, I think phase 1 here. Is this one being done in phases? Actually, I take that back. That's the second project I'm talking about. This one has 2 buildings complete already. You can see them in both the images. So on the 2 sides of the image are the 2 apartments that have been finished, and in the middle is kind of like a clubhouse for the center. That's the one that has the solar panels on it. So this is 2 buildings of apartments, 72 units total. They did 2x6 wood frame, dense pack, 2 inches of polyiso they used on this one. You can see the other details that they did there. A very impressive project here as well. A lot of great things going on. So I wanted to show you this one, as I thought this was a very good one to see. Let's see, and then we have this one, the Tyler. So this is actually a retrofit and sort of a what did I want to say? This was an adapted retrofit. So this was an old high school that was converted into an apartment building, and this was certified through the ENERFIT program, which is what PHI uses for retrofits. So this was really impressive that they were able to do this, kind of take this old brick building and retrofit it into a passive house apartment complex. In this case, it was senior housing, so 70 units of affordable senior housing. Fantastic example, and really thrilled to see it. Columbus Commons. So this is the one that's currently going on. This is phase 1, which is completed. They also are working on a second phase as well. But this is affordable housing units and sort of mixed use space on the bottom. So it's kind of mixed use commercial space and different things around the bottom. But the main floor there are 80 units of affordable housing. Do I have an image here? Yeah, so I want to show you. I just want to show this image just to give you an example of a slightly different air barrier membrane they're using. This is Blueskin, Henry Blueskin, that they're putting on the outside. It looks similar to what you might see from SIGA, for example, in those other projects, but it's just a different air barrier membrane that they're using. This gives you some example of projects that are going on now. These are Connecticut ones. I showed you a lot of Massachusetts ones. We definitely have a lot of time for questions, so I want to get to those. I haven't seen too many come up so far, but if you have them, please ask. I'm going to go through some lessons learned from some project teams now. So these are a lot of folks in Massachusetts that have worked on these projects and lessons that they have shared. So as I go through this, again, ask questions about any of this stuff. I'll kind of go through some of it quicker than others. There's a lot on this slide, for example, but these are some pretty critical things that you should kind of focus on as you're working on these projects. So bring together your team early. Integrated is the key word that everyone throws around because you really want your team to be involved. And when I say your team, it's sort of, I mean everyone. Obviously, you want the architect, you want to get your GC involved as early as you can. I know with a lot of bid processes that can sometimes be delayed, but as soon as you can have them involved, have them. Get a passive house rater or certifier involved right away as well. Work with a passive house consultant or designer. Have an energy modeler involved. Get your mechanical engineer involved as early as possible as well. So getting all these people involved earlier is just going to make a smoother project. It's also going to reduce that cost premium that I mentioned before. Pay attention to critical barriers. So I've talked a lot today about the air barrier and the thermal barrier. You want to make sure those are clear on all your drawings, on everything that you're looking at. You want to make sure that the team on site, so that's your GC's team, that's the subs that are working with them. You want to make sure everyone knows where this barrier is, what the materials are that constitute this barrier, where the seams are that need to be taped, where the transitions are that you need to pay attention to. You want to be able to communicate that very well. I mentioned the mechanical engineer working with them early, but also work with somebody who's experienced in low energy buildings. If you can work with one that's experienced in passive house buildings, that's great. But you don't necessarily need to. You can work with somebody who's experienced in lower energy buildings. The reason for that, though, is just making sure that they know how to size equipment properly. These buildings have a lot lower demand than traditional buildings, so they're going to require slightly different equipment in a lot of cases. You just want someone who's experienced with sizing equipment properly and designing it properly for these type of projects. As I mentioned, well, actually I didn't mention this, but pay attention to the location of compressors. I've showed you a lot of examples of ones on the roof, but also pay attention to the ones on the ground, and pay attention to, kind of snow. We have to care about that. So even the ones on the roof that you've seen were usually raised up a little bit. That's just kind of giving them a little break from being covered in snow. Some other things down there you can kind of read. I mentioned the excessive solar heat gain, the energy monitoring. I'll mention a little bit because this isn't required by the PASSIVEhouse standard to do energy monitoring, but it's recommended by pretty much all the project teams is to design some type of energy monitoring system in. We want to track the performance of these buildings. We know they're performing really well from the ones that we have seen. We want to be able to have that data, share that data, and show how successful these buildings are. So figure out energy monitoring, kind of figure out some system to use. Apartment compartmentalization. Sorry about that. So that's sort of the unit-to-unit air tightness. We've seen a lot of projects actually run compartmentalization testing. So they'll do a blower door test on different units to actually test the compartmentalization air tightness. This doesn't need to be that 0.6 ACH50 that you see on the exterior envelope, but it is going to be tighter than you're seeing traditionally in a lot of projects. And that's becoming more important as we focus on indoor air quality and ventilation. It's making sure that these units, especially when they have their own unitized ventilation system rather than a shared ventilation system, that air isn't transferring from unit to unit. Kickoff meetings. So this came up on a few teams as well, just mentioning that this is a method of kind of getting at the communication problems we see a lot come up, is just making sure that the GC, making sure that the subs, making sure everyone's on the same page. So they would just have kickoff meetings with the different trades who are there that day. They would review, what was on the sequencing for that day, for that week. Review what are the critical barriers that were being impacted by that. Where was, the air barrier being influenced by this? What were some issues to go around doing that? They used mock-ups on site. So Finch Cambridge did this a lot. They had a mock-up on site. That way they could use that to review things like taping the air barrier, or how to get the air barrier wrapped around the window properly. Things along those lines that they wanted to make sure were being done right. And then invite a manufacturer rep. So this could be the rep from the air barrier company, the rep from the window company, from the mechanical systems company. All these folks are willing to come to your site and help make sure these things are being installed correctly and being done to manufacturer specs. And that's important. Things like, for example, whatever air barrier system you use, the thing that you've seen common in all of these is that the seams are being taped. And a lot of times the tape that you use matters. Different air barrier systems will recommend different tapes being used. And they'll recommend a different amount of pressure being applied to that tape in order for it to stick properly. So kind of following those specifications, using the right tape, applying the right amount of pressure. A lot of cases they recommend a roller that you use to put it on there. These are things that you want the team to be aware of. So mock-ups are a way to sort of show people how to do that, and manufacturer reps are a way to sort of have folks there to make sure that the information is being done correctly. And know your air barrier. This is redundant. I mentioned this a lot of times today, but it's redundant on purpose because this is, as I mentioned, when we get into multifamily projects, larger ones especially, this is the most important factor of hitting the PASSIVEhouse standards, making sure the building is airtight. So this is an example of a drawing here just showing you this is actually the Tracy Community Housing Project that we looked at earlier from McClay Architects. This is just showing you an example of how they highlight the air barrier, how they communicate what it is, how they point it out. But this is important. And whether whatever air barrier system you're using, the sort of critical areas, in this case, you're kind of seeing the roof there, the parapet there. You're also seeing the sort of wall to floor connection there at the bottom. All these kind of areas are the critical kind of junctures that you want to zero in on and make sure you know how that air barrier is wrapping around those junctures. And you want to make sure that the folks who are not only installing the air barrier, but working on anything around that area, any type of sequencing that's going on around that area, they're aware of that air barrier and they're aware of how not to disturb it or how to install what they're putting on over it properly. And then kind of continuing on the air barrier, the way it's tested against a blower door test. Obviously, this is done at the end of the project in order to see if you meet the PASSIVEhouse criteria. But quite honestly, teams are doing this more than that. In fact, we see the recommendation to do this at least 3 times. I've seen a lot of projects do this 4 or 5 times, but 3 times is generally the recommended thing to do. And this way you're identifying air leaks early. So for example, if you do it, full envelope test, once you have windows and doors installed, you can sort of get an idea of how you're doing on air tightness, and you can identify leaks early before you cover up a wall. For example, you can identify if there's a leak through it. I've also seen projects do it before windows or doors are even installed. When you do that, you have to temporarily, block them off, putting some plywood over them or something, and taping that, and making sure that you're kind of creating a temporary blocking system, there, temporary window or temporary door. You also want to block off, penetrations that are coming through that aren't yet sealed. So you want to make sure you're kind of doing that. So there is some prep work that goes into this. So you want to make sure that this is something that you're planning for in your timeline of the project. So when you're going to do these tests. It's also a good idea to make sure different people are on site for when you run these. So having your general contractor, project manager there, or site supervisor on site where you're kind of doing this, having your PASSIVEhouse rater or certifier there can kind of help to really make sure you're identifying things in air leaks. We've seen people use smoke testing. So this is where you pressurize the building and use a little smoke gun to kind of follow the smoke. I've also seen people use fog machines. So you kind of fill the area with fog, and then you can see on the outside of the building that fog kind of coming out. So there's different methods to identify those leaks, but it's important to check that out. All right. So thank you very much for today's session. Thank you to Eversource and Energize Connecticut for providing this. I left a lot of time for questions today on purpose. I think we have until till 1:30, so we have about 15 minutes here for questions. So definitely let me know what you want to know more about. I can talk about all these things in more detail, whatever you're curious about.
Yeah, Aaron, do you want me to go through some of the questions that were in the chat log as you were going through?
Yeah, I can't see any questions in the chat right now, so I didn't realize there were any. That's great.
Oh, okay. Yeah, we might not have your settings set up.
I'm happy to hear there are questions. Thank you.
yeah. No, there's a few here. We can start from kind of the first ones that were coming in. So, does the blower door test assume air-to-air heat exchangers are blocked off first, or are there any other accommodations in the standard to accommodate for heat exchangers?
Yeah, you're gonna block them off and turn them off, exactly. And you're also going to so there's a lot to go into kind of the specifications of how it's run, but things like you're gonna make sure the exterior is all sealed, exterior doors and windows are all shut, interior doors are open, so you have air kind of going through the whole area. And then there's going to be some key areas. So I mean, some people have elevator shafts, some have trash chutes. So these are areas that, and really the key is going to be, are these things in the PASSIVEhouse envelope or are they not? Sometimes we see stairwells that are not in the PASSIVEhouse envelope. They're kind of taken out of it, in which case you're going to want that sealed off for the air barrier test. In some cases, those are part of the PASSIVEhouse envelope, in which case you're going to want the doors open to those areas. So a lot of times where that PASSIVEhouse envelope is in your project is going to determine sort of what is being open and what is not when you run that blower door test.
Great. So the next one would be, does the thermal bridging between steel, does it not, or how do we ensure, I guess, that it does not compromise the structural integrity of the structure?
Right. So this might have been getting at when I was showing maybe like those steel beams, and you kind of have that little thermal break there. So it's a good question. So there's a couple of things you want to keep in mind when you're doing this. You're going to be working with your structural engineer while you sort of figure out these problems. So when I mentioned kind of bringing the team together early, I didn't specify the structural engineer as part of that, and I should have. That's somebody you're going to want involved early as well, so you can go through these with them. And then you want to make sure that the material that you're using, whatever these thermal breaks are, they're aware of, that they approve of. So I guess that's basically it. You're working with your structural engineer and running, whatever integrity tests they need to ensure that is going to work.
Got it. Yep.
Yeah.
Another one here. The ERV unit that you had shown on the slide was only has a heat exchanger. I don't see any cooling coils. Do you typically see ERV or HRVs used with heating and cooling to heat the air in winter?
Yes, great question. So yes, and the way it works is they just work backwards. So the heat exchanger does both. So in the winter, you're pulling the exhaust air out of the interior of the space, and generally the exhaust air is being pulled out of bathrooms and kitchens. That tends to be where we see the exhaust being pulled out of, and that's going to be heated air in the winter. That passes through the heat exchanger, transfers some of that heat energy to the incoming air, which is cold. So now that heat energy is being warmed up from some of that heat being transferred to it. That's being put into the building. And it's usually, the incoming air is usually going into the living spaces. So your living rooms, your bedrooms. In the summer, this system is still running. It runs year round. In the summer, it's doing the opposite. You're getting warm air from the outside. So the air outside is warm. The air inside is cold. So the cold air is being pulled, yes, the cold air, the exhaust air is being pulled out of the inside, and then the incoming air that's warm is having heat energy taken out of it and transferred, and that heat energy is being put into the outgoing air. So obviously you don't care if the outgoing air is being cooled off, but that's just kind of where you're dispensing the heat energy from the incoming air. So that cools down the incoming air because you just take some of the heat energy away from it. Does that make sense for folks?
Great, yeah, thanks for that.
Yeah, and just I'll mention in a similar way for heat pumps. Heat pumps just as well. They provide heating and cooling as well. So the ERVs and HRVs, they're providing a method of like transferring heat energy from incoming air to outgoing air, whether that's cool air or cold air. They're always transferring heat, but whether that's going to the incoming air or outgoing air depends on the season. But they're not really providing any. They don't have any heating elements in them that provides additional heat beyond what's already in the air. Your heat pump unit is what's providing additional heating or cooling.
Great. So the next one, what data do we have on VRFs versus individual heat pumps in terms of the operational and maintenance costs?
Yeah, that's a really good question. So I have a slide I'm going to pull up here. I'm going to stop sharing my screen for a moment just so I can find it. I don't think I did stop my screen. There we go. I don't have good data on the cost, so that's not what this slide is going to show. But we are going to look at something here if I can find it. Apologize for one moment. Unfortunately,
slide deck.
What's that?
Pulling this one from a different slide deck.
Yeah, here we go. Just to kind of show you here. All right. Can folks see this here now?
Yep.
Great. So this is just showing you the performance comparison from these different methods. This is again from Peterson Engineering, who helped put this together. But this is showing the performance between centralized, the semi-decentralized, which is the hybrid approach, and decentralized or unitized. So the performance you can see is pretty much all, pretty much similar across the board, whichever system you use. And the bigger consideration, so I'm going to stop showing because that's really all I wanted to show in this case, is based on our these maintenance costs, these operational costs. This is a hard one to get at. I'm sorry, this is not really kind of getting at too much, but it does kind of in a roundabout way, because really your operational cost is in many ways your utility costs, right? It's how much energy are you using, how much electricity are these systems using to run. And what you're seeing is that the KPDU per square foot of these systems from the slide I showed you is about the same, depending on whatever system you use. So what that means is that your utility costs are going to be about the same. So your operational costs based on energy use is going to be pretty similar across the board. The maintenance cost is where it gets a little bit more trickier to answer, because that does change from project to project. And I don't have any really good data on that. I just know that the maintenance is different in terms of how do you access these units, where are they located, who's replacing them, what type of filters are they using, how much do those cost, how often do they need to be replaced. All these things can vary. So that one I don't have a good answer on. But in terms of simply utility energy costs to operate them, similar.
Yeah, thanks. That's helpful. And yeah, there's definitely a lot of variables at play when it comes to the maintenance. Couple other questions coming in. Someone noted that it was their understanding that polyiso can permanently lose its R value if it does get wet. For that reason, they tend to avoid using that on walls and reserve it only to roofs when it can be put underneath a continuous membrane. Do you have any comment or perspective on that?
Yeah, I haven't heard too many issues about that, so I can't comment if that's been happening in projects. I do know, so this is, kind of true of other materials as well. You have mineral wool, sometimes put on the outside. Mineral wool will get wet and will kind of have water in it. The key that we're seeing in all these projects, whether they're using polyiso or mineral wool, all the examples I showed you, is having that air gap between the insulation and the siding, and that allows these materials to dry out. So the bigger issue is, say, if you have mineral wool and it's allowed to stay wet, you're going to reduce the thermal insulation potential of that. And same thing with polyiso. But if they can dry out in a timely fashion, you're not going to have that impact. So I don't know exactly, the details of how much water, damage does polyiso need before you're going to have sort of a critical performance impact. But by having that rain screen, having that gap there and allowing it to dry out, you're kind of avoiding that in some ways. And you're also, if you notice, the polyiso that I showed you is foil phase. So that foil phase being put on the outside also kind of helps protect it from getting too damp on the inside.
Yeah, that's helpful. Thank you. So this is a good question around incremental costs, Aaron, where you mentioned that the incremental costs aren't necessarily as high as some people perceive, and particularly with some of the examples in Massachusetts, that may be attributable to the fact that the building code in Massachusetts is so robust, so that projects don't have to go that much further to reach PASSIVEhouse standards as compared to maybe some other states. But you didn't mention an example or data from Pennsylvania showing a similar trend. So the question is the baseline in Pennsylvania similar to that in Massachusetts, or were there other factors, variables at play that sort of account for that lowered incremental cost that they were seeing?
Right, great question. So I don't have a slide on the Pennsylvania stuff, so I'm going to just kind of explain it and what I'm referencing. So Pennsylvania, their affordable housing financing agency was the first state finance agency in the country to incentivize PASSIVEhouse. So their QAP, similar to what Connecticut did later, is they gave extra consideration to PASSIVEhouse projects. So they got extra points in the sort of financing consideration, and they did this early on, around 2015, 2016. So the data that was kind of gathered from this was taking a comparison of affordable housing projects that went through this financing and got approved, and comparing the ones that were PASSIVEhouse projects to the traditional ones that were not PASSIVEhouse projects. And what it showed is that there was ranging from about a 0 to 2% cost comparison from the PASSIVEhouse projects to the non-PASSIVEhouse projects. In the first year, it was a little bit higher, it was closer to that 2%. In the second year, they had numerous projects that were at that 0% cost comparison to sort of the traditional ones. So that just kind of gives you an idea where the data is coming from. So we're talking about affordable multifamily projects. Where that baseline is, though, that's kind of the really excellent question, because what it's getting at is what are we comparing it to? And that's, I think, important for not just cost, but important for some of the performance data as well. Obviously, as we talk about improvement over traditional building, what is traditional building? What are we modeling that? So that's just something to keep in mind for all of this. And I'm talking a lot about it just to kind of get away from the fact that I don't have a good answer for that for Pennsylvania. I don't know what their base code is. Massachusetts' stretch code is pretty strict. So those who are talking about the stretch code here, that is correct. I showed you a couple of the slides, I believe was referring to the stretch code, then I had a couple to the base code. So that wasn't actually the stretch code. So that might kind of be more similar to what Connecticut has, the base code versus the stretch code. But for Pennsylvania, I don't have a good answer on what their kind of base was, but it's simply the traditional projects that we're going through affordable housing financing compared to the PASSIVEhouse ones. Are folks still there?
I think he's on mute.
Oh, yes.
Yeah, I'm talking to myself on mute. I was just saying if the person who asked that question has any follow-ups, we've got some time left here in the Q&A, so please feel free to chime in. We did just get.
Oh, and as you kind of look at the question, I'll just mention that there's some really good data on that Pennsylvania stuff put together by Tim McDonald from Onion Flats. They're a design build developer in Pennsylvania or in Philadelphia who's responsible for a lot of those projects. And he's done some really excellent presentations where he talks more in depth about that. So if you can find some of the Tim McDonald Onion Flats presentations, you might get some more answers about what they're comparing, kind of what those cost premiums are in Pennsylvania. Sorry, go ahead with the next question, Keegan.
Yeah, no, I was just gonna say a good one came through. Yeah, so what is the official Passive House position when it comes to embodied carbon? And the person asking notes that there are a number of examples today of insulation and other products that require petroleum in their production or have otherwise high embodied carbon in their manufacturing. So what's the official position that Passive House takes?
Yeah, great. Excellent question. We've been more and more concerned with embodied carbon over the last couple of years, especially this year. So first of all, I'm going to give you my interpretation of the official position because I don't speak for them to give you the official answer. But my interpretation of the answer from both of them is that it's not built into either standard. So whether you're going for PHIUS or PHI, I mean, if you achieve Passive House, the embodied carbon. So just so everyone's on the same page, when we talk about embodied carbon, in this case, we're talking about the energy required to build and transport the materials used in construction of the building. In some cases, also the end of life waste of those materials, but generally just that kind of first section of manufacturing and transport of those materials. So that's not accounted for in either the PHIUS or PHI standard. It's simply operational energy as opposed to the embodied carbon energy. However, both standards are looking at embodied carbon, kind of figuring out ways to address that and ways to incentivize projects to do things like this person was getting at, which is using better, lower embodied carbon materials than other ones. So for example, I showed you some projects using mineral wool, and I showed you some using polyiso or foam boards on the outside. Mineral wool is a lot better in terms of embodied carbon than those foam boards and the polyiso boards. So I mentioned one project I think talking about Finch Cambridge, where they did mineral wool. Then I showed you the same architecture firm worked on that project in Gloucester, where they went with they went foam boards. And they did that because of some of the specs for the exterior siding that they went with, but they tend to prefer mineral wool because of embodied carbon reasons. So they have kind of this desire to do it, but it's not always practical to do that. And it's not required by Passive House. I do know that PHI, through their modeling software, the Passive House planning package, they're introducing sort of a ribbon, as they call it, but simply a way to include embodied carbon in some of the calculations. So if you're using the Passive House planning package to do your energy modeling, you can have some level of embodied carbon modeling in there as well. But while that's there, it's for informational purposes, it's for your, to influence your design, but it's not a requirement of the standard yet. I hope that in the future it will be. But it's currently not a requirement. But we are seeing more and more, attention being paid to it. And I think the desire to use low embodied carbon materials is there. The reality is, in a lot of cases, we're still using too much spray foam, too much foam boards. So trying to get away from that has proved challenging, but I see the intent is there.
Yeah, really, it was a really good question, and definitely a hot button issue that's becoming more and more on the top of the discussion when it comes to these topics. So we have about 2 minutes left, and I think we have a good closing question here. Is there a central repository or a database that people could access in terms of general contractors or builders that have worked on these projects or demonstrated interest or aptitude in working on these types of projects?
Yeah, that's the question. So I'll point to a few resources that are out there, and a few because there's not a central depository. So we'll just kind of give you a few different resources to use. So first off, there's the kind of organizations like Passive House Connecticut and Passive House Massachusetts, or sorry, Connecticut Passive House Massachusetts. Our websites both, I think, list, have some information on contractors there. But then you have the certification organizations, so PHIUS and PHI. So what you can find through their various websites is you can find the firms that have Passive House builders or Passive House trade persons. So I mentioned they have accreditations. So a lot of GCs will have people who go through either the Certified Passive House Trade Person course or the Certified Passive House Builder course and become certified through these organizations. And both of the PHIUS website and the PHI sort of site will list who those people are. So you can sort of identify some people who have at least been certified that way through those places. So those are sort of some methods to get at it. And then both of those organizations also have their databases of certified projects. And they will generally show you information about the project teams. So just like some of the slides I showed you today had some information on the GC. In a lot of cases, they will have information on who was the general contractor for the project, along with other things like who was the mechanical engineer and other things. And that way you can kind of get an idea of who's working on some of these projects. So those are some of the resources that you can use. We're trying to get a better central database, and I know at our end of Massachusetts, through our website, we're trying to get a better way to kind of just show you all the different folks who are working on this. But those are some of the places you can look at the very least. And I would say what we're seeing is we're seeing a lot of new contractors kind of get into this place. So you have sort of some experienced folks now, but you're seeing a lot of people kind of who are new at this, who are able to do it. They're able to do this on their first project. I think the key is, working with, someone on your team who's experienced, whether that's you at the architecture firm, that's the developer who's done a few projects before, working with an experienced PASSIVEhouse consultant, whoever you kind of work with. If you have a GC who's dedicated to doing this, they're going to figure out how to do it. If they care about achieving PASSIVEhouse, you're going to help them, and they're going to figure out how to get their team on board with this. They're going to go through some of the training. We've seen a lot of teams do innovative on-site trainings, involving these mock-ups and other things. There's lots of ways to sort of get teams up to speed. So don't limit yourself to just the folks who have done this before. Find somebody who cares about this, and they care about achieving. If they care about the craft of building, they're going to care about building a really high performance PASSIVEhouse building. They're going to figure out how to hit this with you.
Yeah, thanks, Aaron. And that takes us right to 1:30. So,
Right.
Yeah, thanks to everyone who joined us today, and special thanks to Aaron, for presentation. Anna, the recording will be available when and where?
Hopefully by the end of this week, it'll be sent out in a follow-up email to everyone. So stay tuned for that email.
Great. Thanks again, everyone. Thanks, Aaron.
Thank you.
Thank you.
Bye.